All right, so we're going to start into Module 3 and talk about what is some of this digital LMR technology we've been talking about. And we're going to talk specifically about 3 types of digital LMR technology. I know there's many others, but within the US, there are 3 that have come to predominate. P25, DMR, and NXDN. You may have heard of some others, Tetra, DPMR. Those are primarily other countries, other continents. They're out there. We're going to have some signal identification, and I've got some audio files out here that I'm going to try playing. And last week we didn't have a lot of luck with them. Today I'm just going to play them through the speaker, and hopefully you'll be able to hear them better. And so we know that there's a lot of different digital modulation. There's no way I could possibly talk about them all in one day in one slide set. So that's why I'm focusing on these 3. So we know that there's LTE, CDMA, IDEN, a lot of different things that you know about digital modulation. But these 3 are probably going to be the most widely used in the USA. So first of all, why did we make this move to digital in the first place? Analog was a great technology. Why did we have to? We didn't have to, but why are we moving to digital? Well, a lot of things drove that. First of all, data is becoming the big driver for it. Voice is great, but people are sending data and they want to do it over their radio system. One of the things that digital gives us is higher immunity to interference. The bandwidth capacity is probably the biggest thing that drove us to digital. When the FCC said by 2013, everybody in Part 90 has to be digital, I said, well, that's really hard to do in analog, so we're going to make a big push to digital. But that's a good thing because it provides enhanced features. It provides us error detection, which we don't have that capability in analog. Gives us better security. Now we have the ability to easily encrypt signals. We had the ability to encrypt in analog, but the problem is the encryption systems that were available in analog also reduced the coverage range. So because we're using a native digital technology, it makes no difference to the coverage whether we're encrypted or not. And one of the biggest things is the consistent audio quality, and we're going to demonstrate that in the graph. Computer technology. Now we're able to leverage all the advances in computer technology. When we have infrastructure, we can use commercial grade items, switches and routers and servers that the computer industry uses, and we don't have to develop specific proprietary devices anymore that we can use off-the-shelf equipment. So all the technology advancements are happening in the digital domain, so that's why we want to go there. So if you look at this slide over here, this is a graph of audio quality versus signal strength. Now generally, intuitively, you would think, well, the higher the signal strength, the better the audio quality. And that was certainly true in the analog world. As you get further away from the transmitter, your signal got weaker and your audio quality went down until you reached a point where it just wasn't any good anymore. It was too weak. In digital, it takes a slightly different path. In digital, what will happen is the audio quality will remain good further along the way as the signal gets weaker and weaker because of error detection and correction. Even as the signal is weaker, the audio quality will remain good for a longer time until finally you reach a point where it's just not good enough, and then it rapidly drops. So the curved line in this graph is our digital audio quality signal strength, whereas the dotted line, straight line underneath it, is the analog linear function. So we see that we have some audio quality improvement. We get a much better signal over a longer distance before it finally falls off. And you've probably seen curves like this before. So what is it that makes a particular radio digital? I've identified 5 different things on this slide, and we're going to talk about these in more detail after the break. But we're going to talk about the fact that what makes a radio digital is it's going to have digital modulation. It's going to have reduced bandwidth relative to analog radios. It's going to require a specific type of multiplex technique to get multiple users on the channel. It's going to have a vocoder to turn analog voice into digital. And it's going to employ some form of error correction so that we can have that enhanced coverage due to error correction. We're resuming talking about what makes a radio digital, and we talked about that these 5 parameters are what identifies a radio as being digital. Its type of modulation, its bandwidth, how it's multiplexed, how it's vocoded, and whether it has error correction. So we're going to talk a little bit more about each of these. Digital FM modulation. Well, there's a lot of different ways to do digital modulation. We're going to talk about some of them in detail. Others of them we'll just mention in passing because there are simple digital modulations and there are some very complex digital modulations. The ones that are used in land mobile radio are relatively simple compared to some of the ones used in cellular and some other type of services. So some of the types of modulation you'll see, frequency shift keying is a very simple type of modulation, not used for voice, but used for digital bits, ones and zeros. K is a variation on frequency shift keying that rather than shifting the actual carrier frequency, it uses 2 audio tones, each one representing a 1 or a 0. Then we have the most common type of digital modulation that we'll encounter in LMR, which is called 4FSK, or also known as C4FM. That uses 4 different frequency shifts, each shift representing 2 bits of information. So because each shift now represents 2 bits of information, we can double the effective bandwidth relative to FSK or AFSK, which only represent 1 bit per shift. So we'll see C4FM used in the 2 predominant types of modulation out there, that being P25 and DMR. However, that's P25 phase 1, which is still the most common being used. There are other types of FM that use 8, 16, 32, or 64 tones. And that by using more shift levels and tones, they're able to fit more bits in and increase the throughput. Those get pretty complicated and aren't used much in mobile radio. Other things that you may hear about, GMSK is a reduced type of FSK modulation. Quadrature amplitude modulation, where we're actually amplifying or modulating the analog levels as well. And QPSK, which is used in P25, modulates both amplitude and frequency. So before we get too caught up on modulation, I'll tell you that our Module 7 is all about digital modulation, where we focus on the ones that we actually will see in the field. Let's talk about 2 terms that often get confused, bit rate versus baud rate. So bit rate is bits per second, the actual number of bits, also known as the raw data rate, sent or received. Baud rate is different because it represents the rate symbols transmitted over the air. Now a symbol can represent multiple bits depending on the type of modulation. We mentioned that C4FM, every shift level represents 2 bits. So that has a symbol rate, which is 1/2 of the bit rate. So depending on what type of modulation we have, it can we can have a different baud rate than bit rate. For the very simplest type of modulations like FSK, where each bit represents a 1 or a 0, the bit rate is the baud rate. But in more complex modulation, the symbol rate will be lower than the bit rate. And as we said earlier, in C4FM, we might have a raw bit rate of 9600, but the symbol rate, or the baud rate, is actually 4800 since each symbol represents 2 bits. So the more sophisticated modulation, the lower the symbol rate relative to the bit rate. And this animation was showing in the drawing how it goes through. So beyond the modulation, now we have the multiplex methods. How do we accommodate users on the system? And there's a couple different ways that gets done. The simplest and most common is called frequency division multiple access, where each channel of traffic is represented with a specific frequency. So one frequency, one channel. Time division multiple access takes it to the next level by packetizing the bit rate, dividing it into time slots. By doing that, we can then increase the capacity by alternating and slicing in time each of the channels. So for instance, we can have a 2-for-1 increase if we put two time slots in every channel, or a 4-to-1 increase. We have 4 time slots per channel. And technologies are out there that do 2-to-1, 4-to-1, 6-to-1, and beyond. So DMR and over in Europe, Tetra, they use TDMA. Also, of course, phase 2 of P25 uses TDMA. There are other types of multiplex methods primarily used in cell phones. Code division multiple access, where we have spread spectrum and pseudo-random noise codes and all that, which we won't get into today. Also, another method is called carrier sense multiple access that allows channels to share, but if there's a collision, it will have collision detection and retry. But again, FDMA and TDMA will be the two that we'll be focusing on. So here's the difference graphically between the two. On the left, we have one channel per carrier, and the modulation, it could have different bandwidths. Like there's GMSK at 6.25 kilohertz bandwidth, FDMA with C4FM at 12.5 kilohertz bandwidth. And on the right shows a TDMA diagram with 2 time slots, like we would see for P25 phase 2 or DMR with a 2-channel per carrier time slots. So every couple packets is a new time slot, and then you reassemble the packets in the receiver, and to the user there's no change. You don't hear any choppiness because your ear and your brain is able to reconstruct it perfectly. How's the bandwidth compare with some of these different modulations? Well, on the top we have some analog modulations, single sideband, which is used mostly in the HF bands, has a bandwidth of about 2.7 kilohertz, a lot narrower than used to seeing in the FM world. If it was double sideband, that goes to about 6 kilohertz. Our analog FM, which was our predominant method years ago, 16 kilohertz bandwidth. Today, with the reduced bandwidth and digital modulation, the European style DPMR has a 6.25 kilohertz bandwidth. The DMR and P25 that we see in the US has a 12.5 kilohertz bandwidth. So you can see how some of these bandwidths compare to each other visually. We talked about a vocoder. Vocoder stands for voice coder decoder. It is a set of software and firmware embedded in the radio that whose job it is to convert our analog voice into ones and zeros for processing. It's made possible because of the digital signal processing chips, the DSP chips that are available today that can provide complex algorithms to do that. The challenge in vocoder has always been not to do the conversion, but to make it work in a very narrow bandwidth. Because when digital music came out, like compact discs came out in the 70s, they used a method called pulse code modulation, where each level of the analog signal was represented with a digital code. Well, you can see that would represent a lot of bandwidth, and it works on a CD where you have megabytes of data, but it doesn't work so well over the air. So it was not considered for over the air modulation. But with the rise of DSP and all the signal processing capability, vocoders have improved greatly over the past 20 years. Primarily, there's one company that's got the license for all that technology, a company in Boston called Digital Voice Systems Inc., DVSI. Do most of the coding and development of these vocoder technology and license them to the manufacturers. So over the years, they've come out with 3 primary vocoder families. The first one that came out was called IMBE, and it worked okay, but if you ever used one of the early digital radios, the digital wasn't that great. It was hard to tell who was talking. As time went on, they came out with better vocoders, first with the AMBE product, and most currently with the AMBE plus 2 product, which is currently used with DMR. And these are much better compared to the original digital vocoders. You can actually tell who's talking, and in some cases you forget it's digital. So what are some of the digital standards that are out there today? Well, it depends on where you look. There's been development in the North America, but there's been different standards developed in Europe and Asia and Australia. And so while these technologies are used all over the world, there are certain technologies used more in certain areas than others. P25 is primarily used in North America, US, Canada, Mexico. It was by APCO and the Telecommunication Industry Association. And of course, we talked about phase 1 and phase 2, FDMA and TDMA standards. And the leading manufacturers for that have been Motorola and Harris, who used to be Maycom, and going way back used to be General Electric. And then there's EFJ, which is now part of JVC Kenwood. DMR, which we're going to talk about, digital mobile radio, started life as a European standard, European Telecommunication Standards Institute. Motorola took and built their Moto Turbo product line around it. There's lots of other manufacturers making it. That's a 2-slot TDMA technology that we're going to talk about. Another product that was developed under a European standard was called DPMR, which is a narrower bandwidth type of technology similar to DMR for low-cost commercial applications. And the primary manufacturers of that have been Kenwood and ICOM, which are two Japanese manufacturers. NXDN, which we're going to talk about also, is similar to that, but uses a protocol that's proprietary to Kenwood and ICOM that they call NextEdge and IDAS. That has started to take off somewhat in the U.S. because its cost has gone down and it has a narrow bandwidth. You may hear reference to something called Tetra, which is the European public safety trunking standard. It stands for Trans-European Trunked Radio Architecture. Based on the European standard, and the leading manufacturers are Motorola in Europe and EADS. But that's how it is today. If we give this talk in 10 years, there'll probably be some new alphabet soup of new digital standards that are being developed. So some of these didn't exist 20 years ago. So it's constantly evolving. So you got to keep on top of it. And again, we talked briefly about P25. It's not a standard, but a set of separate standards. The public, anyone can see them. There's nothing proprietary in there. It defines voice and data digital LMR architecture. Primarily, it was developed for public safety first responder groups in North America. That was its target audience. Several industry groups were involved. APCO, Association of Public Safety Communication Officials. So it was originally called APCO Project 25. Also, the National Association of State Telecommunication Directors, which is why it's so common for statewide trunk systems, because the state directors were involved. TIA, which is the industry group for telecommunications. And the leading P25 manufacturers are Motorola, Maycom, which is now Harris, and they've had several name changes over the year. Currently, they are Harris, EF Johnson, which is JVC Kenwood, Daniels, which is now part of Codan. So you can see, with the exception of Motorola, these companies keep changing their name. One of the primary drivers for P25 was the fact that the FCC mandated that Part 90 users had to go narrowband by January 2013. Now, have to go? Well, non-Part 90 users, and that would be your marine radio service, which is regulated on a international basis, so was exempt. So the VHF marine channels are still 25 kilohertz. And also the amateur radio service in their 2-meter and 440 bands still can operate in 25 kilohertz bandwidth. But all the Part 90 users, which includes public safety and commercial users, had to go narrowband in 2013, which drove the need for P25. Its purpose, you had to have an open standard, because what was happening in analog trunking was every manufacturer was doing their own thing, and they were proprietary protocols, and they couldn't each other. Well, the big thing in public safety is interoperability, and you can't have that if every manufacturer has a proprietary protocol. So P25 opened it up to a standard. They all signed on to it, and now they can interoperate. Also, it provided competition, which drives costs down, allows better interoperability, so that this county system can talk to that county system, which can talk to the state system, which can talk to the federal system, which can talk to national systems, and they can all interoperate. It also provided improved spectrum efficiency relative to the analog predecessor. So what's in the standards? There are different documents. We talked earlier about the Common Air interface, the very basic level non-infrastructure interoperability parameters. But then taking that to the next level, you have to talk about conventional systems, how do they interoperate? Trunk systems operate. Some of the things we talked about. What's the control channel data rate? And what's the control channel signaling protocol? Dispatch. Whenever you have first responders, you have dispatchers. You have to have interfaces between the radio system and the dispatch. RF subsystems. How do the various space stations talk to the system? Interoperability. How do systems from different manufacturers communicate with each other? Intersystem. How do systems interoperate at the system level? How do their infrastructures tie together if they have to? How do you bring data into the system? So all that is addressed in P25. And as we mentioned, the first one that came out, it wasn't called phase one, but when it first came out, which is now known as phase one, the standard called for a 12.5 kilohertz bandwidth and interoperability with analog systems that were operating at 25 kilohertz bandwidth. So it had to have backward compatibility. And then when phase two came out to increase the throughput and the user capability, now we have 6 equivalent channel bandwidth. Now we're still using 12.5 kilohertz actual bandwidth, but because we're fitting 2 users into that, our equivalent bandwidth is half of that, or 6.25. And phase two also introduced time division multiple access. Now moving into the phase, there will be more specifications about high-speed mobile data. So this first kicked off in 1993, called Project 25. Again, those are some of the bullets there are some of the things that we talked about that Project 25 covers. And trucking was one of those standards. So we talked about this on an earlier slide, so I won't go into all the same detail, but the Common Air interface is the radio to radio interoperability. It includes the type of modulation, the data rate, the type of error correction, the bandwidth, the type of vocoder, the type of encryption. The first encryption that was specified was DES, the data encryption standard. Today it's AES, advanced encryption standard, which is a much improved type of encryption, and it had to be backward compatible with analog equipment. Phase two, as we said, came along much later when it was decided that they needed more capacity. So that's when TDMA was introduced, although it still had to be backward compatible with FDMA. It introduced 2 new types of modulation, one on the inbound side and one on the outbound side. Since vocoder technology kept advancing, the state of the art at that time, and we're talking about 2000s, was AMBE. The control channel stayed the same, voice channel at 12 kilobit, data, fail soft talk around. We mentioned all that previously, but that's what phase two provided. So what happens inside a P25 radio? Well, on the transmit side, you've got your microphone, and it goes into an A to D converter. This is your vocoder. This is the device that turns your analog voice into bits, along with the speech coder. And that will then push it into the bandwidth of the channel, which is the function of the channel coder. The baseband filter will ensure that it fits in the required bandwidth. The modulator will then take that signal and modulate the RF carrier through mixing it with the voltage control oscillator in the mixer. The combined and mounted signal then goes out to the amplifier and then through the duplexer to the antenna. On the receive side, just the opposite happens. The incoming weak signal is amplified. It's mixed to create the intermediate frequency. It's demodulated, filtered, and goes through a vocoder in the opposite direction, producing voice at the other end. So what are some of the features in P25? The first thing people notice when they pick up a P25 radio is the red button on top, or orange button. What's this thing do? Well, in most cases, it's programmed to be an emergency button, so that if the first responder gets in trouble, he pushes the button, it sends a signal over the control channel and signals the dispatchers and all the other radios. It comes up with his ID and tells them he has an emergency. That was an original feature of APCO 16 back in the 80s. Call alert, which is the ability to signal a specific radio, kind of like paging someone. Radio status check, and we're going to talk about these in the upcoming module with digital features, but just some highlights. Radio status check to check someone's status, basically a ping feature. Radio inhibit, to disable a radio. The network access code, which is the digital equivalent to your PL code. The ability to support data, and the ability to support encryption. So encryption was provided as a P25 feature, but it's an optional feature. You can choose whether to use it or not. One of the reasons P25 took so long to get off the ground was it had to allow compatibility with legacy equipment so that the same infrastructure could support analog radios and digital radios. Today, that's not as big a thing because almost all the users are digital, but that was an original requirement of P25. Again, spectrum efficiency was what drove this whole process, that the old analog systems operate with a 25 kilohertz bandwidth, and with C4FM in P25 phase 1, we were able to reduce that to 12.5 kilohertz, and then further reduce it with CQPSK to 6.25 kilohertz. We'll talk about those modulations. But again, FDMA reduces the bandwidth by reducing the deviation in the frequency domain. So the reduction came when we moved from 25 to 12.5 kilohertz. TDMA took it to the next step and split that 12.5 into 2 time slots, giving us the equivalent of 6.25 kilohertz bandwidth. So that's P25. The next thing we're going to talk about is DMR. It's a big thing coming in. It's been around for a long time. DMR stands for Digital Mobile Radio, and it is as common in the non-public safety world as P25 public safety. There's a lot of this DMR equipment going out there today. It's based on the European Telecommunication Standard Institute standard. So it's the way to think about DMR is it is the predominant digital standard for non-public safety users. Originated in Europe, but now extensively used in the US and around the world. Not to be confused with DPMR, which is a different narrowband standard used by ICOM, Kenwood, and some others. So what is DMR? There's the ETSI standard that created it. There are 3 tiers that are described in the standard, or 3 modes of operation. Tier 1 means your direct mode, radio to radio, no infrastructure required. Tier 2 is your conventional operation through a repeater, and Tier 3 operation is trunking. So it can support all those different modes of operation. The frequency bands in use are anywhere from 30 megahertz up to 1 gigahertz. So they make DMR equipment all over the band. The access method described in the standard was 2-slot TDMA. So remember this came around 2007, so TDMA was an established technology by then. The bandwidth of DMR, 12.5 kilohertz, same as P25. The modulation, 4FSK or C4FM, same as P25. 9600 bits per second, same as P25. So you see there's a lot of similarities between DMR and P25. The vocoder is more advanced because it came along later, and this is the most current vocoder technology out there, AMBE plus 2. And the vocoder, not the raw data rate, but the vocoder operates at 3600 bits per second. And the data packets, it supports IP data packets, as well as short data and messaging protocols. So it's similar to P25, except it's used in non-public safety applications. It doesn't have all the critical emergency features that P25 has, and it doesn't cost as much either. So this DMR was developed in the 2000s, 2005, the standard was created, and then in 2007 they published 4 new standards to cover the air interface, the voice, the data, and trunking, the different tiers. So some of the technology used in DMR is similar to P25 terminology, but there's a few distinctions. So we talked about the fact that TDMA uses time slots. And again, DMR, just like P25 phase 2, uses 2 time slots. A radio ID, just like P25 radios have an ID. In DMR, each radio has a 7-digit ID, which is unique to that radio in that system, used to identify and authenticate users. Same as P25 does it. Talk group, same thing that P25 does. A predefined group of users normally communicate with each other, and you can have multiple talk groups existing on each channel independent of each other. Now here's a term that is unique to DMR called the color code. And think of this like a NAC code. It's a digital code used to identify a particular repeater. So it's similar to PL in the analog world or NAC in the digital world, but color code is a DMR term. Code plug, and this term is also used in P25, is basically a firmware configuration file that is used to program the subscribers. Talk around, this is also used in P25 when you have no infrastructure and you just want to talk radio to radio using the output frequency of any one of the repeaters for direct mode operation. So you can see there's a lot of similarities with P25. TDMA, we talked about this earlier, but uses time slots. So 1 and 2 shared in the same system. And I see I got a question on the chat, and I'm going to answer that during the lunch break. Okay, because we're moving on, but I will get to that question. Okay, so again, 2 time slots in DMR. The channel capacity, again, 2 TDMA channels are created within the same 12.5 kilohertz channel. There are systems out there that use 4 TDMA channels, some that use 6, but the concept's the same. So you now have the ability to support 2 channels in one repeater. And it effectively operates like 2 in 1. One of the features of DMR is that for the portable users, they have improved battery life relative to things like P25. And the reason is when you are using time slots, you're really only transmitting for half the time. So since you're only transmitting half the time, you use almost half the amount of battery. And so it's typical to see a 40% improvement in battery life relative to FDMA radios. And as a one-for-one comparison, the same type of battery that will support 9 hours in analog will actually take you to 13 hours in DMR. DMR, just like P25, has data capability, very similar in that mostly uses third-party applications to do it, and it just provides the carrier to support data. So just like P25, every user has its own unique caller ID that comes up when you receive the call. You can do text messaging on it. You can do third-party applications to support GPS location. The radios themselves are available with built-in GPS receivers. They can do telemetry. They can do simultaneous voice and data. And one thing that's unique about DMR is you can either put voice and data on separate time slots, or you can combine 2 time slots together to get an improved data rate for data. Also, a lot of people don't realize, but DMR can also support wide area systems and do trunking. So because we have a second time slot, we can do some other things that previously could never be done in analog. We can use the second channel as a management channel or a control channel so that we can prioritize calls. And this is actually done when we do DMR trunking. We use a time slot to effectively a control channel. We can do things like remote transmitter controller shutdown. So if a transmitter gets locked up or something, we can still access it by the second control channel, by the second time slot, and shut it off. We can also do things that we typically associated with trunking, things like emergency call preemption, where we prioritize some calls over other calls for access. We're going to talk more about this in the modulation section, but DMR, just like P25, uses 4FSK, or also known as C4FM. And this diagram shows that in the legacy type of audio frequency shift keying, we had 2 audio shifts off of the center frequency at 1200 and 2200 that represented a 1 or a. Well, with C4FM, we have 2 shifts plus and minus from the carrier frequency, giving us a total of 4 possible shifts, so each one can represent 2 bits instead of 1. The vocoder, as we said, was the device or the software that turns voice into digital. When it was first created, no specific vocoder was mentioned, and they would allow that whatever the current technology could be used, and that's currently called AMBE+2 vocoder, which operates at 3600 for the voice to data conversion. Well, who makes this stuff? Well, there's a lot of different manufacturers in DMR. Far more people make DMR than P25 because it's used in more places around the world. So you got the Chinese, the Italians, the Japanese, all involved in New Zealand. They all make the stuff. Hytera. There's several other Chinese manufacturers whose names I can't pronounce. Celex is an Italian brand. Tate out of New Zealand. Motorola makes their Moto Turbo product line, which is Moto Turbo is just Motorola's trade name for their DMR product. And that's used in the US and all over the world. Vertex is a Japanese company. ICOM Kenwood and Vertex Standard. They're making DMR. They're also a Japanese company. There's a US company called CSI that makes DMR. So you can see there's a lot of people in this business. And the last technology I'm going to talk about is called NXDN. And that's the newest player in the scene. It's narrowband. It's an open standard. It was developed specifically to go narrower than the other technologies. It has the capability to operate in two different modes, either in a 12.5 kilohertz bandwidth mode or a 6.25 kilohertz bandwidth mode. So NXDN was developed jointly by Commdex and Kenwood, both Japanese manufacturers. There's not a lot of it today in the US, but more is coming online because it's relatively cheap compared to P25. It's a competitor to DMR. It was actually adopted by the Association of American Railroads to replace the old VHF 160 megahertz railroad channels. But the railroads didn't really like it that much. It didn't do a lot of things they were used to. So it hasn't been widely accepted, even though their industry group required it. But we'll see how that develops. But it's good technology. As I said, there's two different flavors of NXDN. It can operate in 12.5 kilohertz, or you can go to 6.25. So there's a spectrum plot of the two-channel TDMA with, well, no, that's not TDMA, that's FDMA. The two-channel FDMA NXDN with, you can see how the two channels are adjacent to each other, each one being 6.25, and it fits within the 12.5 kilohertz emission mask. So that gives you a 2-for-1 increase in FDMA as opposed to TDMA doing the same thing. So there's different frequency shifts used here for their type of C4FM, but it's the same idea. Each deviation represents. And here is the second mode of operation for NXDN, which is a single 6.25 kilohertz channel, showing how it fits within the 6.25 kilohertz emission mask on a spectrum analyzer. And now Tetra is something that you probably won't see in the US anytime soon. It was developed in Europe, called terrestrial trunked radio. It was basically the European version of P25, and it uses a more cellular type approach with lower power transmitters over a wide area. So same target market as North America did for P25, But in addition to Europe, it's also used in the Middle East, Africa, Asia, and Latin America, and I believe Australia as well. The main thing that's different about it is it uses 4-slot TDMA, but in a 25 kilohertz bandwidth, which is why it's not being used in the US, because it requires 25 kilohertz bandwidth, and we're only allowing 12.5. It does it with 4 slots, so the effective bandwidth is still 6.25, but it wouldn't be allowed here because of its bandwidth. It can operate in trunking or direct mode, capable of voice and data, supports encryption, wide area roaming, and uses an IP infrastructure. So I was involved in Motorola in several Tetra systems, and the interesting thing about it is it uses different base stations and radios, but the infrastructure that supported it, all the IP infrastructure and the dispatch consoles, were exactly the same hardware that was being used in P25. So companies like Motorola that were in both markets were able to leverage their technology developed for P25 to serve the European market. So the next couple slides, which will wrap up this section, I'm going to provide some signal identification. We're going to look at what does P25, DMR, and NXDN look like on the spectrum analyzer. And specifically, these images came from an Anritsu S412E LMR spectrum analyzer, LMR master, which you may or may not be familiar with the Anritsu, but we use it a lot in the field to as a field spectrum analyzer to do transmission line sweeps and lots of other things. It's not a full vector system analyzer, but it is a great field spectrum analyzer. So we're going to show the spectrum and the waterfall plots, and I'm going to try to play some audio files so you'll be able to recognize these signals when you hear them. So what we're going to do on the audio files is, last week they didn't come out too well. This time I think I'll just play my speaker and hopefully you'll be able to hear them that way. So we'll see how that goes. So first we're going to look at P25 phase 1. This is again the spectrum plot as seen on the Anritsu 412. Over here is, with the colors, is called a waterfall plot. You may or may not be familiar with a waterfall plot, but this is used on a lot of the software-defined radio receivers that are out there. It's a nice way of looking at spectrum versus time. It falls like a waterfall. The red colors being higher signal levels, and the blue being lower signal levels. So you can see how this corresponds. The red corresponds to the peak, and it allows you to see spectrum versus time. And so I'm going to try with this audio file. I'm going to unplug my, let's see, I'm going to unplug my headset and play this through the speaker, and let me know if you can hear it okay. Okay, was anyone able to hear that? Give me a yes or no if that worked for you.
We heard a little bit break in there. It sounded just like the static, which you would expect.
Yeah, P25 is pretty much sounds like static. Okay, we're gonna try the next one, DMR, and this This happens to be the single DMR signal, not the twin one. So this is the waterfall plot, and I'll try again with the audio. Okay, I hope you could hear that one.
Yeah, that was a little better.
Okay, I don't know if it's better. It's kind of more annoying than the P25, but let me go back to the P25 and turn the volume up a little higher, see how that sounds. Okay, and DMR again. Okay. All right. So hopefully you heard both of those. And finally, we're going to look at NX. Did I do NXDN yet? Maybe I didn't. No, I don't think I did. NXDN is next. This is the narrowband NXDN. You can see the waterfall relative to the DMR. It is narrower. So this is the 6 1/4 NXDN signal. So we'll try playing this for you. Okay. Hopefully you were able to hear how that sounds different. Were you guys able to hear that last one?
Yeah, it was faint. Sounded different than the others.
Okay. All right. Gives you an idea of the different types of signals. And just to wrap up this section, here is a summary of the different types of systems that we talked about: analog, FM, P25, phase 1, phase 2, DMR, NXDN, DPMR, and Tetra. As far as their modulation, their bandwidth, how many channels per carrier, the type of vocoder, the raw data rate, and the access method. LTE, LTE, I'm not going to say a lot about it. It's out there. It's a separate technology that was developed primarily for the cellular market. I only mention it in that there are systems out there like FirstNet that you'll hear about that use LTE, and there are subscriber devices that will incorporate both P25 LMR services and LTE services within the same radio. And the picture is what they call the APX Next radio that Motorola makes that works on both services. So that's the last slide for this section, and we'll take our third break.